Hey team, welcome to the numbers game. I'm Coach T, and in this tutorial we're going to be proving continuity of a function. Now before we get started, make sure to subscribe to the channel for notifications on more math tutorials. Alright, now let's take a look at this example. In this example, we're given the piecewise function f of x equals x squared if x is rational, and f of x equals 3x if x is irrational, and we're being asked to prove that f is continuous at x equals 0 and x equals 3, and f is discontinuous at x does not equal 0 and x does not equal 3. Now in this tutorial, we will focus on proving f is continuous at x equals 0. We'll cover f is continuous at x equals 3, and discontinuous at x does not equal 0 and x does not equal 3 in part 2 and part 3 respectively. And I'll include the links to those tutorials in the description box. So to prove f is continuous at x equals 0, we'll use the epsilon minus delta definition. So here it is. It says that for all epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus f of a is less than epsilon. So we're going to use this epsilon minus delta definition to prove that our function is continuous at x equals 0. Now before we get into the actual proof, we're going to need to do a bit of scratch work first. Now the point of doing scratch work is to find a delta that ensures our claim is true. That is, at point x equals 0, for all epsilon greater than 0, there exists a delta greater than 0, and that's the delta that we're going to find in our scratch work. So there exists some delta such that the absolute value of x minus 0, so we replace the a in our definition with our point 0, needs to be less than delta, and if it is, then the absolute value of our function f of x minus f of 0 is less than epsilon. So again, the point of doing scratch work is to identify a delta that ensures that this claim is true. And once we've identified a value for delta that satisfies our claim, we're going to start our formal proof off with assuming delta equals whatever we found in the scratch work. So we're starting off with point x equals 0, and also notice that we're given a piecewise function. And in our piecewise function, we have two conditional statements, and this means that we're going to have two separate cases. The first line in our piecewise function says that f of x equals x squared if x is rational. So let's start off by doing scratch work for the first case, which is that x is rational. We'll start the scratch work off with the absolute value of f of x minus f of c. And c equals 0, so then we've got the absolute value of f of x minus f of 0. Now our piecewise function told us that if x is rational, then f of x equals x squared. And then when we plug x equals 0 into x squared, we end up with 0 squared, or just 0. So therefore, this simplifies down to the absolute value of x squared minus 0. This just equals the absolute value of x squared. And that's enough simplifying, and so I'm going to say this is less than epsilon. Now, if the absolute value of x squared is less than epsilon, then the absolute value of x is less than the square root of epsilon. And we got that by just square rooting both sides here. So again, we've got the absolute value of x is less than the square root of epsilon. And the square root of epsilon is what we're going to set equal to delta. So that's the scratch work for our first case, x is rational. And now let's do the scratch work for our second case, x is irrational. Again, we'll start off with the absolute value of f of x minus f of c. Here c equals 0, so that's the absolute value of f of x minus f of 0. And in the case that x is irrational, f of x equals 3x. And then when we plug x equals 0 into 3x, we get 3 times 0, which equals 0. So from here, we can simplify to the absolute value of 3x minus 0. 3x minus 0 just equals 3x, so that's the absolute value of 3x. We'll move the 3 to the outside of the absolute value, so that's 3 times the absolute value of x. And that's enough simplification, so we can say this is less than epsilon. Now, if 3 times the absolute value of x is less than epsilon, then the absolute value of x is less than epsilon over 3. And we did that by dividing 3 on both sides. So we've got the absolute value of x is less than epsilon over 3, and epsilon over 3 is what we're going to set delta equal to. So we'll combine the delta we found in the case where x was rational and the delta we found in the case where x was irrational to get delta as the minimum of the square root of epsilon and epsilon over 3. And now that we've finally identified our delta, we can start our formal proof. Of course, we'll start off with all epsilon being greater than 0. Then for all epsilon greater than 0, we'll set delta equal to what we found in the scratch work. That's delta equals the minimum of the square root of epsilon and epsilon over 3. Then for the absolute value of x minus 0 is less than delta, we have the absolute value of f of x minus f of 0, which equals the absolute value of x squared minus 0. This equals the absolute value of x squared. And we know that this is less than delta because in the scratch work we saw that delta equals the square root of epsilon, and the square root of epsilon is less than epsilon. Now before we move on to case 2, I want to take a moment to pause and explain what I'm doing. In our proof, we need to directly follow the epsilon minus delta definition. It says for all epsilon greater than 0, there exists a delta greater than 0, which we found in our scratch work, such that if the absolute value of x minus a, which for us is the absolute value of x minus 0, is less than delta, then the absolute value of f of x minus f of a is less than epsilon, which we have shown in our proof. So this is how you execute a proof using the epsilon minus delta definition. All right, now let's move on to case 2. We'll start off with the absolute value of f of x minus f of 0. This equals the absolute value of 3x minus 0, which equals the absolute value of 3x. And we'll move the 3 to the outside of the absolute value, so that's 3 times the absolute value of x. And this is less than delta, which equals epsilon over 3. And epsilon over 3 is less than epsilon. So at this point, we've shown that when x equals 0, the absolute value of f of x minus f of 0 is less than epsilon in both cases. And there you have it. We've proven that our function is indeed continuous at x equals 0. If this video was helpful for you, give it a thumbs up, like it, drop a comment down below too, and subscribe to the channel for notifications on more math tutorials. I'm Coach T, and thanks for watching The Numbers Game.